part of your degree. I mean, if your degree says you need COS231, you better be excited about this stuff, because that's what computer science is. I remember one semester when it started, I had three or four people sitting in the back of the room the first night, and I could tell they were really not keeping up with the rest of the class. They didn't ask appropriate questions. They never had a correct response. And it wasn't until the third class, now remember this is in-person third class, that one of them raised their name and asked me if this was the nursing class. They thought they were in they sat there for 3 nights listening to this drivel I give them, and they thought they were in a nursing class, and they were 3 nurses that had just wandered astray and wound up in the wrong place. So I redirected them, and for what I know, they were happy thereafter.
What did they think nursing was?
I can't even imagine what they thought when I said you have to memorize your powers of 2. I think they were memorizing bones in the body or something. Who knows? But you know, when you teach as long as I have, you've seen everything twice. And so that actually was the second time I had somebody in a wrong class, but I'll tell you guys some of the other stories on a different night. We got to get some work done here. Okay, so let me grab my, well, I got it on the screen, don't I? The syllabus. So let me remind you here that participation labs, homework, all this sort of stuff counts up for 50% of your grade. So, you know, I saw one person last class sneak off to his job. Don't do that. You know, you signed up for this class, be here during the class time, and respond when I call your name, and with an answer if you can. Or if you don't know the answer, saying you don't know may have to be your answer. I mean, it's not worth as many points as it is if you did know the answer, but it's certainly better than not answering at all, because if you don't answer at all, I assume you're not at the computer. And that means your participation grade goes down. Attendance counts as participation. At the end of the semester, I have this monolithic program, huge thing, that knows how to go in and get all of the times that people were signed on to the system, including the times they were dropped by the network. Chop off the time they were here before class, chop off the time they were here after class, basically add it all up and put it over the number of hours they were supposed to be here. And from that, I can derive a number of points to see how much participation you get out of pure attendance. Of course, the stuff like you were here early and you were doing productive stuff, or you were here late and did productive stuff, that doesn't count for that participation, but that certainly would count if I need to be swayed with some extra credit at some point. For example, if you wound up right at the line between an A and a B. If I knew you had been participating and I saw active, effort in the class in that sense, you probably would get it rounded up as opposed to just truncated. And I can't guarantee that. I mean, there may be other reasons why I wouldn't, but that's one of the things that we need. Now, well, there's one other thing that I've been meaning to ask you guys to do. This is worth 1 question on the first exam, meaning if you do it and you miss a question, I'll just assume you got the question right. What I need you to do is send me a selfie, a picture of yourself. And you may say, why do I need those for? Remember that little program that shows the names? It has a little slot there for your picture to be in it. So I also can, by recognition, know that who you are, and you'll care about that. Not so much because of this semester, but let's assume in 2 or 3 years you finish your degree and you went to NJIT. And remember, I have like 80 students a semester. What's the chances of me remembering you just by name? But if I've seen your name and your picture, I have about twice the chance of it. And you might at that point, call me up and say, could you be a reference? And I might be, if I have good memories of you, or if I have my records show that you did things. So I'll give you 1 test question for free if you'll take a selfie of yourself and email it to me. And make sure it's a picture that you'd be proud of. Don't take a picture of you riding a dog or something like that, but a picture that I would be able to recognize you in a professional setting and, be able to say, yes, I know who that person is. So that's your first little chance at a little piece of extra credit there. Is one of the test questions on the first test If you miss it, I'll give it to you as having gotten it right if you have sent me a selfie. Okie dokie. Let's see how we're doing on people. We got 23. We need 25. So 2 people are still out wandering the streets somewhere. Don't know where, but when is tonight? We finished up capacity. Well, we didn't finish them up. We started beginning talking about capacitors, and we learned some things. We'll review some of that tonight. We did not yet talk about the 555 timer. We will tonight, and we'll talk about it with respect to using it as a clock. And when I say clock in computer science, I don't mean tick-tock, tick-tock, I'm 12 o'clock in the afternoon. I just mean a signal that can be used to synchronize other signals. Sometimes it's repeated, sometimes it's not. But we'll talk a little bit, some of the just basic principles of what a clock is before we talk about implementing one. And then tonight we're supposed to begin talking about sequential logic and latches and flip-flops. So those things are on the table tonight as things we should do. I doubt we will completely finish flip-flops, but we'll get a good start on them. Then the next class we have, I guess is next Monday, we'll be talking about counters and shift registers, which are elements, and some other things, which are elements, just like we had digital components up here. These are some more digital components. They just happen to be based in sequential logic. So that's kind of where we are and what we're doing. Again, notice that not too far in the future, exam 1 is looming its head up. And if you think we're doing about 2 units a week, you know, so this would be Monday, that would be Wednesday, that'd be Monday, that'd be Wednesday, that'd be Monday, that'd be Wednesday, and then the exam. But all this stuff is on it, so you would want to even early on start doing some kind of a review. I'll try to schedule an online review session with you outside of class time, but it's going to be really tough because of my teaching schedule. And I also have 2 classes, both of which would need to be able to get to the review because you're going to be tested similarly. And usually I take about an hour and I go over things which I know you need to know for the exam. So it's worth going to. It's usually pretty close to the exam also. So don't assume it's going to be something that, oh yeah, I won't go, somebody will record it and I can watch it later. You may not have time. So beware of that. Okay, so we're going to start out tonight talking a little bit about sequential logic. But before we do that, I want to back up just one little notch. And I want to talk about one of the, or actually a couple of the parameters that had to do with the 7400 chip, the NAND gate we've been working on. If you recall, we've already determined what the voltages are. We've determined what the currents are. What we did that night that we went over these is I specifically said, oh, here's some timing information. We'll skip that until we get to sequential logic. Because so far when we've been talking about combinational logic, we've basically said, whatever the truth table says, that's exactly what happens at the output, at the exact moment we change the inputs. So just with, I got a little paint here somewhere, I guess I do. If I had a truth table, which yields Y over here, and I said, okay, well, this is going to be an OR gate. We made the assumption so far that the pure Boolean algebra formula, which is Y is equal to A or B, happens in real time. And the moment one of these values change, the output changes to the correct thing inside the table. Well, imagine for a second that we took this value at the bottom, 1, 1, and we decided to change it to 0, 0. What's the likelihood that we could, on the input pin even, get those to change at exactly the same moment? Well, it's probably a chance of about 0, maybe slightly better, but one's going to happen a little bit in front of the other. But let's assume that we could get these to change from this to that instantly. Well, on my screen right here, right there, it's probably different on your screen, but about there is about the distance light travels in a nanosecond. Well, an integrated circuit chip is about that big. And electrons move slower than light does. You know, sometimes significantly, sometimes not so much. But the electrons, they still have to get from a pin here, perhaps, to a pin there. So that's got to take some amount of time to occur. So in a real circuit, going from here to here isn't as quick as you might think it is. There could be a delay between the time we change the inputs and the output reflects that. Now, not only that, but if we're changing the output from a 1 to a 0, that may take a different amount of time than if we're changing it from a 0 to a 1. Meaning that even if we were to get the inputs exactly on time with each other, we're going to get the results at a time that's predictable in terms of we can give some worst case and some average times, but there's still going to be a delay between the time it gets here. And the delay is different, perhaps, if we're going from high to low or low to high. This time we have is something called a propagation delay. Let's see if I can write this fast enough. Propagation. The way it'll be abbreviated in the data sheet is with a T. This is not a tau, but a T. Then there'll be a P for propagation. Then there'll be something like an HL, which means what's the propagation delay from high to low? There'll be a value for T, propagation delay, low to high. Of course, if it goes low to low, like 0 stays 0, there's no delay. There actually is, but we don't see it because it's already the right value. And same thing with 1 to 1. You're not going to see the delay, but there is one. It still takes time to recognize the change and realize we still have to put a 1 out. But since the value never changes, we want to make sure that we see that that's not going to be affected by us. Now, one of the things we have to be very careful of is if we have something where the output is a 1 and we change the inputs in such a way that they don't change at the same time, rather we get a sudden drop to 0 and we come right back again. This is because the inputs really were something that generated a 0 during that time period, but it's extremely short. This still may be long enough to launch the missiles. So you want to make sure that you never have something that's going to be honored by a system during the time when it's not stable yet. These things, anomalies, are called hazards. ARDS. Or they're sometimes called glitches. You've heard the term glitch probably. So sometimes we design our circuit to prevent these. There's ways we can use a Karnow map to determine how to avoid that, taking advantage of the adjacency to put some additional circuitry back in. Sometimes we don't go to a minimum sum of products. Some we go to a partially minimum to get rid of glitches and hazards. They're slightly different. That's why I'm giving you both names, but I would accept either one as a correct answer for that. So this is one of the things we care about. So when we go to the data sheet, one of the things we want to look at, besides our voltages and our currents, let's review the voltages and currents for just a second here. VCC on a 7400 chip could range from 5.75 volts up to 4.25. What am I doing? I have it backwards here. Let me wipe that out. 4.75 up to 5.25. And its nominal value is 5 volts. So it wants to be 5 volts, but we'll tolerate slightly higher and slightly lower. Our inputs, remember we have an input for voltage for the input, we have a high, and we have a voltage for the input low. On the input, we will recognize things 2 volts and higher as being a high signal. We'll recognize anything at 0.8 volts and lower as being a 0. So anything between greater than 0.8 and less than 0.2 is in an unknown zone and could be accepted as either one. So we make sure we don't put voltages in there, which means our outputs have to be compliant with that. So the voltage output high and the voltage output low for the particular chip we're working with. The high voltage will never be less on an output than 2.4 volts, which means, of course, it's compatible with TTL inputs because they'll accept down to 2 volts. Also, actually, this is 0.4 volts. I'm sorry. I need to use a maximum there. This is 0.8 volts. So when I'm low, I'll always output at least 0.8 volts, which means the 0.4 that it'll accept is well below it. So our outputs are compatible with our inputs. Now this might produce 2.4 and slightly less or up, but generally we think of it as being up from that point and this down from that point. The difference between the 2 and the 2.4, or the 0.4 and the 0.8, we called that the noise margin. Noise margin, because that's how bad it could get and still be an acceptable signal. The other ones we looked at were the 4 current things. We have the current on an output when it's high. We have the current on an input, on an output, we'll do the outputs first, when it's low. The output when it's high is going to be 400 microvolts, or microamps, which is a small number. The output when it's low is going to be 16 milliamps. And if we were to look that up in the data sheet, for example, let's see, where is it? Here's our input. Oh, this is a different chip. Okay. Our current for the output high is 0.4 milliamps, which is 400 microamps. Notice the minus sign. That matters over here because minus means out of the chip. So this goes out of the chip. This would come into the chip. We call, when it comes into the chip, sinking. We say when it goes out of the chip, it's sourcing current. Now, to be compatible with these, the current on the input when it's high is going to be 40 microamps going out of the chip. No, I'm sorry, I'm lying to you there. Going into the chip, and because it's not got a negative sign. And the input when it's low is going to be 1.6 milliamps. This comes out of the chip minus this. So you could take 10 of these and hook them to one of these, or you could take 10 of these and hook them to 10 of those, or one of these. And what you get is the fact that we have something called fan out. Fan out is the number of inputs that can be driven by an output And in our case, a single output has sufficient current, both inward and outward, to drive a 10 of these values. So if we had another chip with different values, we'd have to count to see what the fan out is. But typically, standard TTL to other standard TTL has a fan out equal to 10. So now we got two new numbers here. We've got to come up with our propagation delay times for a standard chip. Now, standard chip like this, a TTL chip, does not have a clock. Rather, it is going to change when the inputs change, but it'll change based on the propagation delay. So we go to our table, and I think it's on page 7 of this particular chart I have. And we look for our chip. Our chip is an SN7400, so it's this chip. We see here's the time for the propagation, low to high, and time for propagation delay, high to low. And it's the time between A or B changing, or both, and Y reflecting the output. So typically it's going to take, if we're going from low to high, about 11 nanoseconds for that to occur. However, going the other direction is only about 7. Maximum, it could take as long as 22 nanoseconds to change, or in the other direction, 15 nanoseconds. So we probably would use this 22 nanoseconds as a design value. We'd make sure that we never had signals closer together than probably about double that. You don't want to get too close to the actual values. These all are with respect to a particular resistance for the load and the capacitance for the load, which is kind of in all circuits. But it also matters what temperature it is and what voltage you apply. So if you think about processors today, quite often we crank the voltage up and we apply a lot of cooling in order to overclock it. What we're really doing is we're making these propagation delay values go down. So if you've overclocked your CPU, that's what you're doing. And of course, there's a limit. This thing will, little solder joints will all melt if you get it too hot. So you have to balance raising power with the amount of cooling you have available. That's why a lot of these systems are liquid cooled, because it's better at removing the heat. It gets rid of it quicker. But a TTL chip like this has the same issue. If I were able to, instead of 5 volts, I put 5.25, or in the military case, I think it can go all the way to 5.75, then I would be able to run the chip a little faster if I had to. Certainly it would be more tolerant of signal changes. Okay, anybody have any comments before we move on?
You said that the time was usually double the whatchamacallit. Is there a particular reason why it goes? Like, I know you said it shouldn't be too close to the actual number, but is there any reason why it has to be like doubled?
Kinda. We're going to actually talk about that in kind of the next section. So I think it's next. It may be the one after that, but I'll explain it to you. In almost all of the cases, for instance, you remember when we figured our beta out for our base current when we lit an LED? We boosted it twice. So we almost always use kind of 100% over if we don't have any reason not to, because it'll make things run cooler. It'll make things be happier, you know. And so unless we have some reason why we have to approach these numbers, we don't want to approach them. So just as a rule of thumb, you know, simple rule of thumb is let's just double it. But I'll show you a reason why we might want to also in just a few minutes. Okay, so let's talk about what a clock is, and then we're going to review our capacitors again. I think, okay, let's see, I need to start my capacitor review. Yeah, I have a little timesheet off to the side here because we have a lot of stuff to cover tonight. Okay. So I'm going to, I just reuse this. And I know there's a way I can select it all and hit delete or something and get rid of everything, but let's see what happens. That works too. The idea of a clock I'm going to make time run across the screen, and I'm going to make voltage run up and down for now. If I were able to move a switch up and down, so it went from ground, it went up to 5 volts, it went back to ground, it went to 5 volts, and I could do that in some sort of steady fashion. I could use the edge of this particular hump here, or the edge of this one, or maybe the falling edge of this one, or I could just say, well, anytime it's high, or maybe anytime it's low, I want that to indicate to some other part of the circuit that it's safe right now for it to do whatever it needs to do. So you're at a party and you're standing behind the main person, and they're, taking pictures for the newspaper and all that sort of stuff of this, and you're behind the guy and you're making faces. And ever so often, he turns around, looks, and you just real quick get rid of making the face. And then he turns back around, you start making the face again. So when he's not looking at you, it's safe to make the face. When it's not, you better be holding still so it looks like you're making him the guest of honor. Make some more faces. Whoops, here he turned around again, you hold still. So we could kind of think of that conceptually in our system as, let's assume we have another signal somewhere that we want to capture, and it's wiggling around like crazy. We want to make sure that it's being held still during perhaps the whole time this is high, and then we just let it wiggle again anytime it's not high. And then we hold it, maybe it's up here now, and we hold it stable again. And then we let it wiggle, and maybe it changes in the middle a couple times up and down, and by the time it gets here, it needs to hold stable again. Maybe it holds stable for a whole one on its own, but then holds stable while it's high. We can think of this, or this level right here, as being a clock. It's basically telling the other signal when to behave. So we would call this a level clock. Now let's assume that when this changed, somehow this signal now, this guy is input to something else, and so the output has changed as a result of this. The output changed as a result of that. The output changed as a result of that. Notice the output can only change once propagation delay time has gone by, past the time that we actually changed during this period. Now, I might not really at this leading edge of this thing have a signal available yet. I might have just switched it, and it may be changing back and forth a little bit on its own because propagation delay time hasn't occurred yet. It's not until here that it's actually stable. So we want to make sure that the time that we have high is long enough that if I were to look in exactly the middle of the time, I'd be able to capture a piece of data because now it's stable. Well, I could also say that the level could be high, it could be low. It also could literally be an edge. We could say, let's make our circuit so that we pass our input to our output only when we get an edge, only when it's going high, or maybe only when it's going low. And we make sure in our system that we only transfer either on one or the other. Now, do you remember a while ago, let's say we're producing this clock out of some 7400 type of device. Even though we said we're going to make the clock change at this point, we had to manipulate the inputs to cause that to happen. And once we manipulate the inputs to cause that to happen, we know that this doesn't happen right away. Rather, this happens propagation delay, low to high, in the future. Same thing here, as it goes from high to low, we get propagation delay, high to low in the future, before we see the edge. So although we drew it here, it may not happen until there. We drew it there, it really doesn't happen until here. Well, the circuit that's receiving this clock can't do anything until it gets it. So let's imagine for a second that we were to shrink the signal down so that all we really had was enough time for the edges to occur. what we'd see is the time from here to here is the maximum propagation delay time from low to high. This would be the maximum propagation time from high to low. And if we assume worst case for both, and this is 22 microseconds or nanoseconds, this is 22 nanoseconds, this whole time period for this thing right here is double the maximum we would possibly ever use. So we'd never want to use a clock which had a shorter time period for the entire up and down thing of 44 nanoseconds. So a good design rule, of course, as we said last time, was to take this time and double it, which gives us this. Of course, we still would never do that. It's still too close. So the time we'd actually use is bigger than this, but this becomes kind of a minimum we shoot for. We certainly couldn't do it with 22 because it wouldn't have time to change either direction during that time period. So once we've done this, and we have the notion that this is how clocks or a clock could be used, we're going to have a level and an edge. We need to talk about some terms having to do with the clock. Now I can start either low or high, but if I count the high hump and the low hump together, this is called the period, and it's measured in seconds. So this is in seconds. 1 over the period, I'll just abbreviate it, 1 over the period is measured in hertz, HZ, and it's like the car rental place, except it's named after a different guy. And hertz is basically the number of these per second. We call them cycles per second, CPS. But, and as a matter of fact, this used to be the abbreviation for hertz, but hertz came into popularity sometime about the 1970s as being used for all of the inversions of periods. So if somebody said, you know, I go over to the piano, I hit the A key above middle C, and it's A is equal to a frequency of 440 hertz. If we wanted to know what the period of the thing was, we could take, do I have a calculator open somewhere? I do. We could take the 440 and we could invert it. And we'd see that the period of time in seconds that takes is 2.3 milliseconds, 2.3 milliseconds. And so the amount of time we have here is 2.3 milliseconds if we want to have a 440 hertz signal. So if you're sitting down with your Arduino at the end of the semester, your AT Mega, and you say, I want to make a synthesizer, well, one of the things you're going to need is the tuning note. There's a tuning note in the United States of an orchestra. You'd have to produce a clock which ran at this frequency, 2.3 milliseconds. Now, the other interesting thing about it is now that you know that time, could multiply that times the speed of sound, and you would know how long you had to make the pipe on the organ in order to produce that pitch. So there's a lot of stuff you could do with knowing periods and hertz and things like that. Importantly also is the amount of time it is high versus the total time. This is something called the duty cycle. Now, when you stop giggling, it has nothing to do with bicycles. So the duty cycle, if they're exactly the same, if this is half of this, is 50%. Sometimes we want a signal which is maybe shaped like this, where maybe it's only on for 10% of the time. That would have a duty cycle of 10%. So we can control the percentage. We also could have one, you know, that was off just a little bit on a long time, off a little, on a long time. That might be a 90% duty cycle. If it's on all the time, it's a 100% duty cycle. If it's off all the time, it's a 0% duty cycle. Basically, the clock is not running in either of those cases. So those are some terms we need to know when thinking about clocking. But a clock does not have to run rhythmically like that. I can have a signal which simply at one point during the entire execution of my program goes high. And I can use that as a clock to control something else. The important thing is the clock is telling something else when to do something. That's the key thing. So this could be it runs automatically, or like up here where we're throwing the switch up and down, or we could take something like a 555 timer chip to drive a signal like this. There's a number of things we could do, or we could get a crystal, an oscillator. I mean, there's any number of things that we could use, a resonator, any number of things we could use to generate the clocking signal. Now, you see big fancy numbers, in the gigahertz on your desk side computer, which this clock is having to change like that. They're normally crystal based, and they can be very, very, very precise frequencies at very high speeds. Sometimes they're divided down to slower frequency internally on the processor in order to do specific things. But the external processor may very well have, a 4 gigahertz processor running it or clock running it. And you could determine what the, amount of time for each cycle is. And if you assume it a 50% duty cycle, you could just take this and, divide it by 2. And that says this is how long, it's high versus how long it's low. This would be 1.1 milliseconds here. Assuming I did my arithmetic right, that would be a useful thing to know and tell. Okay, so let us move ahead. Let's talk about the 555 timer. But to talk about that, we need to do just a real quick review of the capacitor. So let me, I think I already have it open. Give us a picture of a capacitor's charge and discharge graph. We know how to compute tau. I can't write the Greek letter lowercase t here, but I'll use a t here. And it's in second, and it's equal to R times C. R in ohms, C in farads. Farads were named after Michael Faraday, and ohms were named after George Ohm, I think his name was. So we need that, and the result will be in seconds. We normally use a lowercase s for seconds because capital S means something else. And so normally you'll see me abbreviate that as S. Sometimes I'll slip up and use uppercase, but I'll try not to. But when we compute one of these, we know how long it takes our chip either to charge or discharge 63%. So if we start at 0, we'll be at 63%. If we're doing discharging, we'll be at 37% after one T thing. These are called, remember the little letter is called tau, but they're called time constants. Notice that a time constant doesn't care what the voltage is. So if we were to take and somebody gave us a problem, they said, I have a capacitor which has a value of 0.1 microfarad, and I have a resistor equal to 1.1 K. Put the K with the ohms over here. What is tau? And secondly, how long does it take to charge the capacitor? Which is basically rewriting that. What is the total charge or discharge time? So let's work that problem. Try to work it yourself and stick the answer into chat. And give me a little green light when you've done that. Let me get you started here, and some of you are having some trouble, I can see. We have to write this in farads. So it's not milli, not micro, but it's 0.1 of that. Put that number back together again. That would be the number of farads that capacitor has as a value. 1.1K would be 1100 ohms. Because I can't write the Greek letter omega, capital Omega, so I have to write ohms. So how do we find out what T is? We wrote the formula up here. It's R times C if R is in ohms and C is in farads. So you get your grocery store calculator out. Put this number in it. Multiply it times that number. And we'll see it takes 110 microseconds. So now we have to answer what is the total charge time? Well, this is 1 tau, takes us to 63%. We saw in our picture here that it takes 1, 2, 3, 4, 5 to get to 100%. So we can take this number times 5, and it'll become a 550 microseconds. Now, assuming I did my arithmetic right, those were the two answers you would need to give me. Anybody have any questions about that? I'll check the chat later to see what you guys put. Unfortunately, the chat is on a machine that I can't see from here. Okay, so let's just brainstorm here for just a second. If it took 550 microseconds to charge this capacitor, Vinod, how long would it take to discharge the capacitor?
Would you divide it by 5?
Well, I
Find out the
wouldn't.
answer?
I wouldn't. Let's see, that was you. Your name came up twice. Alexander, what do you think? How long does it take to discharge one that takes 550 microseconds to charge?
I'm not sure.
Okay. Nicholas?
Would it be 550 microseconds?
You win the prize. You're the first guy in 2 nights to get that question right. My entire class lasted through every individual and nobody got that question right. If it takes 5 to charge and it takes 5 to discharge, and all they are is 5 times t, and both of them are 5 times t, we would expect the answer to what it charges to always equal what it took to discharge it. Or at least to me, that seems kind of obvious. So congratulations. You can have something nice out of the refrigerator tonight when you go rate it.
I'll be sure to do that.
Okay, do that. Now, let's think about this for a second. That means that if I were to repeatedly charge and discharge this thing, let me grab something I can draw on. And that doesn't look like it. It was this beautiful piece of art here. And let's assume that, whoops, where'd it go? We could repeatedly do this over and over again. Somehow. We haven't even said how yet, but let's assume we could. We would be able to go, oops, not a very nice curve, but we'd go up, we'd come down. We'd go up, we'd come down. Kind of building shark teeth here or something. Should have waited to Halloween to do this. But had I drawn these nicely, what we would see is the distance between there and there equals the distance to here, equals the distance to here, to there. So that is 1 unit, that's 2 units. If I were somehow able to sense that I had hit this low point and generate a low signal until I saw this high point, and then switch and generate a high point until I saw a low signal again, and then switch. Can you see how I'm generating what, obviously they're the wrong width and things, but I'm generating basically a 50% duty cycled square wave. There's one period, there's the second one, which is identical. Low and high times are the same. So if I could somehow monitor this from 0 all the way up to the top, and I could sense the fact I got to the top or I got to the bottom, then I'd be able to flip back and forth on this clock, and I would have a nice square wave that I could use to drive other circuitry. Well, we're going to talk about a chip called the 555 timer. Starts with an NE normally, or an NA. So it's an NA, or let's say NE was the one we got, I think. And it might have a packaging information at the end, like it's in a PDIP package or something like that. But it's an 8-pin chip, very standard. I guarantee you, if you go to the space shuttle, you'll find some of these installed in the electronics on it. Very common, very old. It's not TTL, however, it plays well with TTL. So we can drop one into a TTL circuit without much trouble. NE stands for Signetics, believe it or not. And Signetics was bought, I think, by Philips Semiconductor. And today, I think many of these are made by Texas Instrument, but they didn't rename them because this is such a familiar name in part lists. And so it's called a 555 timer. A little side story. It's kind of a, shows how dumb people are sometimes. Back at the turn of the century, between 1999 and the year 2000, people thought the world was going to end because suddenly the century number flipped over from 19 to 20. And everywhere dates were written, like Christmas on this last year would have been 12/31/99. But the next Christmas would have been, not 31, we'll go New Year's then, New Year's Eve, 12/31/20. I'm sorry, 00. I think of this year's 20. And this rollover caused a problem because people didn't know, and all the dates that started in 1900 had 00 there. So we entered a real serious time of computer problems. Everybody was hired to work on the year 2000 problem. And it was to fix all the programs out there that didn't know how to treat the year 2000 and the year 1900 differently. And it's been partially solved. It's going to break again, I think, in 2036 when their solution finally overflows again. But, you know, quite honestly, I'm not going to worry about the year 2036. I think I'd be several hundred years old at that point. But not really. I'd be a little older. But you guys will all be around for that. So you'll be probably part of the people that have to do that. But what happened was, which made it kind of ironic, is somebody saw the name of this chip, the 555 timer. And they realized this is in most of the electronics in the world today. Certainly anything digital has some of this stuff in it. And there was a huge panic because they didn't know how to fix the year 2000 problem in these chips. And you know what? There isn't a problem. This doesn't maintain calendar time. This simply maintains bits. And the bits don't mean anything. They just simply, it's how you interpret them. And so there was no problem. But there were a lot of people that really, made a lot of money off saying they could go fix this. It's like people that make money, selling stuff that stops baldness. We know that's not going to be something you can do the way they, you know, wear this baseball cap full of laser beams and you'll suddenly start growing hair. Well, you might grow hair because of other reasons. Okay, so let's talk about the 555. I have its data sheet here somewhere buried away. At least I think I do. Did I open it up already? I did. 555 timer normally looks like this. It has 8 pins. It does not have 5 volts on the top right and ground on the bottom corner. Ground happens to be up here on pin 1. So it's slightly arranged differently than a TTL chip. Modern times chips, you have a whole bunch of these. By the way, NC stands for not connected, not North Carolina, as one of my students told me. So these same pins are all present here. And it's not until we look inside the chip that we actually got an appreciation for what's going on. So let's look at kind of a diagram of what's in there. And I have to introduce you to some new parts. And although we're not going to study them in great detail, we'll study them enough to know what they do. Okay, so here's the deal with the 555 timer. First of all, we recognize this guy down here as being a transistor, right? It is. Here's the base, here's the emitter, there's the collector. The entire purpose of the chip, the way we're going to configure it, is to turn this transistor on and off and connect the top of an external capacitor to this discharge pin. So we're going to charge the capacitor until such time as we turn on the transistor, at which point it will discharge what's on the capacitor. Since we can compute the charge and discharge times, we can make a predictable square wave on the output. These two guys right here are devices. Notice they look like inverters, but they have 2 inputs. These are called comparators. They're a form of operational amplifier, and we don't need to know the details of them. But basically, in the case of this particular one, it's trying to detect if we go below some value that has been preset here. So we have a preset value, and if the pin called trigger ever goes less than that, it's going to push the S button over here. If it ever goes higher, it'll stop pressing the S button. However, there's another point here that's attached to this comparator, that if we ever get higher than the threshold pin, this guy will push the R button here. So it's going to make us stay with the voltage once we've gotten past the initial turn on, which starts at trigger, goes to threshold, drops back down again, goes back up again. But remember, we're going to externally be charging a capacitor, which is what we're going to measure with these 2 pins. Now, what are these 2 values here? Well, if we go from ground to 5 volts, and we have equal value resistors, that means the value right here is 1/3 of VCC. The value right here is 2/3 of VCC. So if we can somehow externally charge and discharge a capacitor so that the value on the capacitor remains between 1/3 and 2/3 of VCC, every time we drop slightly lower, we'll push trigger. Our trigger will push S. Every time it gets above threshold, it will push R. By the way, this stands for set. This stands for reset. We have an external reset, which could be used to keep the chip from operating at all. So we'll wire it high so that we never have that pin pushed. We also have this control pin, which we're not going to hook up, which would allow us to vary whether this is really 2/3 of the voltage or not. So think of these voltages not even being present. Now, what's going to happen? If I push set, the output becomes a 1. It's inverted, meaning this becomes a 0. And the transistor is turned off, meaning we can not discharge the capacitor, meaning the capacitor now would be able to charge itself again. Eventually, it'll get high enough that it passes threshold. We'll push the reset button. The reset button will make this be a 0, which inverted will be a 1. And the 1 will be high enough, 5 volts, to cause this transistor to turn on, meaning the capacitor could now discharge through the transistor. All the while, this guy is inverted again in an inverter. This is just an inverter we drew with the bubble on this side instead of that side. It's going to cause the output to be a 1. So while we're discharging, the output's going to be a 1. While we're charging, it's going to be a 0 on this particular one. Now, some of them are built so that this, in the sense of this, is exactly backwards, but we're going to pretend like now that it follows exactly the diagram we hear. But the output is going to be a square wave now, reflecting whether we are set or reset. This device right here is called a latch. It latches itself being set or reset depending on which of these two buttons was pushed last. Now let's hook up some wires to that thing. We're going to hook it up in a particular configuration, and there are two major configurations you're going to see. And again, with holes, you're laughing. There's something called an astable multivibrator and a monostable. I know astable and monostable are funny words, but a monostable, which we're not going to use, basically says when we apply a voltage to the proper input on the 555, its output is going to stay high. It's going to go high and stay high for a set amount of time. We could use it, for example, to debounce a button. A noisy button produces a lot of little quick signals. So we would push set a bunch of times. But since pushing it once is good enough, it'll stay that way. We'll never cause a problem with seeing it again. We could put a time period, like maybe after you push the button, even if the guy releases it right away, or even if he holds it, but there's little lightning bolts in the button, we're only going to see one high signal because we'll use the monostable multivibrator connections to force the output to stay high for maybe a tenth of a second. And by that time, all the noise has died down. We instead are going to build what's called an astable multivibrator. The astable does what we want it to do, which is generate a square wave. It happens to have a duty cycle that's not 50%, but we'll see how we deal with that. So here's the wiring we would use. Again, we're not going to use pin 5. We're not going to use pin 4, but we would wire them up anyway. Don't worry about the capacitors that are here or here right now. They're simply to help reduce noise. And don't worry about the fact that what we're trying to do is light up an LED over here. We just care about what's coming out the output. So we hook 5 volts up to pin 8, which is VCC, and we hook ground up to pin 1. Internally, remember, we have that resistor ladder, which has 0 here, VCC here, 2/3 of it here, and 1/3 of it here. And we're going to try to capture it so that it stays between the 1/3 and the 2/3 marks. Now, I actually put an old-fashioned one here. This is a single resistor here, so that we're measuring the thing as being 1 or 2. Actually, no, the one we just looked at. Didn't I give you the one that was double resistors? Yeah, 3 resistor one. Okay, I'm thinking of a different chip for the moment. But we got 3 voltages here we can hook to. So, as I said, we're going to hook both trigger and discharge, or trigger and threshold, to the top of a capacitor. Notice it's polarized. It has to have the positive side on top, negative side on the bottom. And we're basically on those 2 pins going to measure whatever voltage is currently on the capacitor. We're going to take 2 resistors, RA and RB, and hook them to VCC. So we've got a path to charge the capacitor. And as we start to charge it, it's going to eventually make it all the way up to 2/3 of VCC. Threshold will detect that. Internally, the transistor will be turned on, and this discharge will be hooked to ground through that transistor. Notice where the discharge is. It's at the top of the capacitor on the other side of this 1 resistor. So the moment that opens up, instead of charging, the capacitor will start discharging through pin 7 until it drops below 1/3 VCC, at which point trigger will detect that, and it will punch the set button on the latch, causing this to close off again, and we'll start recharging. at which point this will start charging up toward threshold again forever. So we'll constantly either be charging or discharging. Notice that the reason we can't have a 50% charge time is the time it takes, or tau, for charging, T sub little c here, is equal to the resistance, which happens to be Ra plus Rb. Times the capacitance. Whereas our discharge time, let's call it T sub d over here, is equal to simply Rb times the C. So we know that our discharge time is shorter than our charge time. Now, depending on whether or not we're high while we're charging or we're low while we're charging, that means we'll have an asymmetrical duty cycle. It can't be 50%. So we could go to the data sheet. And you might go, well, I could easily calculate what the charge and the discharge times on that would be because I know it's tau times. Well, the problem is we're not going from 0 to 5 volts, or to whatever, we'll say 5 volts. We're not going from 0 to 5 volts. We're going from 1/3 of 5 volts up to 2/3 of 5 volts. And then we're discharging from 2/3 down to 1/3. So this would not be an easy calculation. We'd have to sit down and do a whole bunch of math to figure out, using that exponential curve we have, how much time we need. Since we don't want to do that, we're lazy, we would go to the data sheet. We would find the section on applications. We don't want to operate monostable. We want to operate astable, so we would not hook it up this way. Instead, we'd hook it up the astable way, which is the picture I just showed you, basically. And on the next page, we would find the formulas. So the amount of time that we're high is 0.693 times tau. That takes care of the fact we're only going from 1/3 to 2/3. And when we're tau for us, when we're going low, is going to be the same thing, but only times Rb. So we can see right now that the duty cycle is higher because we're high for the longer period of time. Now, if we wanted to literally figure out what the period is, we could just add those 2 times up and invert it. But we also, which they did here, they said here, but we also could work the whole problem, which is 0.693 times what's basically the 2 taus added together times C. So adding these up and inverting it gives us exactly the same thing as having done this. Or we could take, if we wanted the frequency and still do that calculation, we'd need to divide that into 1.44 instead of 1. But these are some other useful relationships. Duty cycle is time low over high plus low, which is basically the ratio of B over A plus 2Rb. Remember, we go through Rb on both the charge and the discharge. And we also could look at the waveform to see the duty cycle of the waveform. This is when we're the amount of drive time we have. This is the entire thing taken. So we have that. And then a little chart over here to help you pick out which resistor and which capacitor you'd want to be using. And then we go into one of the other uses it can be used for, which is missing pulse detection. So we're not going to worry about that. We're going to only worry about astable operation, which is in this little application note. I may or may not post this. Remember, I'm posting things that are handouts under lessons on the Blackboard. Make sure you went there. I added a bunch of things between Monday and tonight having to do with the material we had covered. And some of this stuff will get added tonight for you. So that's how a 555 timer works. We're able to now produce a square wave that we could use if we need something to be clocked. We also talked a little bit about what a latch was, because a latch turns out to be a very useful device as well. What it's saying when we're using a latch is, I have 2 inputs. One of them is a set, the other one is a reset. I want to be able to push one of those two and cause the output to do what I just said. I want it to set it or reset it. Pushing reset while it's reset should leave it reset. Nothing should happen. Pushing set when it's set already should do nothing. If I push the one that it's not right now, it should change it. But if I don't push either one, it shouldn't change. It should stay however I left it. So we've actually kind of accounted for 3 states out of a truth table. We'll talk about those when we move into the next little section, which I think I want to do right now, which is we want to talk about deriving chips that may or may not use clock, but are useful in the sequential world as opposed to the just pure combinational world. So let me clean a little of this up. We don't need this at the moment. We won't be coming back to him. We might come back to him, but I'll put the hamburger up. It makes me hungry. And clear that out. And I can let it just fall behind everything. And, oh, look down. Can you see down at the bottom everybody's names go by? There's Azam's name. We're trying to make sure Azam doesn't go to work on us. Robert, keep an eye on him. Got to keep an eye on you guys. Not necessarily the people I named, but the whole bunch of you. Yeah. Okay, so we don't need this. We don't need that. Where'd it go? Oh, it was already on the screen. Don't save. Save. And this guy, do that. And we don't really need that at the moment. Okay, and I think this guy's okay. Yeah. Okay, so let me open my folder over here. And push him off the side. Let's look at a possible implementation that we might use for, we'll look at this corner up here, for something that could do a set and a reset. Okay. I'm using the one right here that has kind of the darker transistor on the left. What we're going to talk about with this is a little bit of thinking about the design of this thing and what we really have. I build this circuit, okay? I got 2 resistors hooked to 5 volts, and they're hooked to the tops of a transistor at the collector. And I ground the bases, ground the emitters. And then I take and I hook the collector of one to the base of the other one. I've kind of cross-hooked them up here. Of course, throw in a resistor to limit the current. I also have an output signal called Q. Okay, very Star Trek-y sounding. And what we want to do is we want to try to analyze this circuit to understand what the transistors are doing right now. Okay, first thing I notice is it's completely symmetrical except for this is Q. I'm willing to bet that this is not Q. But I don't know that, so I'll leave it off the picture for now. Let's assume I turned this on. Would the transistor on the left or the transistor on the right be on? Or would they both be on, or would they both be off? Let's take a, let's see. Let me try that. I haven't done that since I was teaching. Oh, this is too much fun. Which takes forever to do. Who in the world ever thought this would be a good idea? Oh, you have to do each one? Oh. I know. I may not want to do this. I'll just ask. I'll ask a simple question here. would both be on. How's that for a question? And let's see what this does. A poll, look at that. So now you get to vote. Wow, I could go make myself a sandwich while you're doing this. See, who says Mercer doesn't have as good a tools as Rider University? I can't do this on their system. I have to use something that would let me ask multiple questions. Still got a few people haven't responded, but I'm getting close to showing the responses here. Last 3 people going to weigh in. Now, it could be those 3 people aren't at their computer, couldn't it? This might be really useful. There's the real responses we got. Okay, so most of you say it would be on, but a goodly number of you say no. And the other, I guess, are going to watch the video. Who knows what they're up to? They're going to miss that participation exercise. And all you got points for that. How about that? Whether you got it right or wrong, you got points for that. Okay, so now what do I do? Oh, I could clear it, in which case you could vote again. Oh, man, that's worth nothing. Okay, everybody give me a green light saying you had fun taking that little quiz. Yeah, see? I knew you were a happening group. Wow, even the people that didn't answer voted yes. I'm loving that. Okay, so the actual answer is only one will be on. And we have to pick which one is on. Let's pick the one on the left. And the reason is, if you think about it, well, let me show you the circuit and then I'll explain that. Let's assume for a second the one on the left is on. I swear I hit green, but maybe I didn't. Oscar, what voltage would I expect to find across the transistor right here? If this transistor is on?
Would it be 0?
0 what? Volts? Amps? Ohms?
Were you asking current?
I was asking voltage.
Oh, then volts, yeah.
Okay. So it'd be 0 volts.
Yeah.
Okay. This is 0 volts and it's on. We kind of have to prove. Let me use green. Actually, let me. This is on. And we've demonstrated, at least Oscar has told us, that this is 0 volts, which is a good answer for when it's 0 volts. Remember, it could be as high as 0.7. Nominally, it's 0.3, but for our purposes, we'll almost always, unless I tell you otherwise, call it 0 volts to indicate it's fully on, saturated. We're going to have to prove to ourselves, since it's on, that there's a voltage here. And Raul, what voltage would I expect to find there? Zachary?
I guess I'll just throw out a 0.7.
0.7 what?
Volts.
Okay, 0.7 volts. Yeah, of course, we're going to have to demonstrate this saturated. So the base emitter of a saturated transistor is 0.7 volts. So that's what we expect to find. Now, if that's the case, that means this 0 volts, there was no drop to get to this 0 here. So it's still at 0 volts there. Meaning that in front of this resistor right here, we're still at 0 volts. And if that's 0 volts, there's no way we can get any current to flow through this transistor to turn it on. So this transistor must be off. Of course, there is 0 volts drop across the base emitter now because 0 to 0 is just nothing dropped here because there's no current, nothing dropped there because there's no current. Transistor doesn't allow any current because it's off. So that means that whatever the voltage is here, minus a small drop there, is going to be the voltage that we're going to see right here. So we can roughly call this 5 volts. So if we have 5 volts through a resistor into the base, we just proved that the 0.7 must be there. We have sufficient voltage to cause a drop here and then the 0.7. So by turning this one on and that one off, we've managed to prove that this point right here would be 5 volts. Now, if this is 5 volts that we have here, that means the Q, which is our output, is currently outputting 5 volts, which we'll just call a 1. So we would say, you know, Q is set. Okay, so in this case, they couldn't both be on because this one being on forces this one off. Let's look at this picture instead. Let's assume when we turned it on, this guy was on. Okay, when we turned it on, he was on. There's going to be a voltage drop across him. So, Noam, what would be the voltage drop across that transistor?
0. 0 volts.
0 volts?
Yes.
You think? You think?
Yeah, I think so.
Okay. And if it's on, the thing we're going to try to demonstrate is that we can get what voltage here, Sumana?
0.7 volts.
Yeah, 0.7 volts. You guys didn't know anything about transistors. You all are experts. Okay, so we got 0.7 volts here. That means we have to be getting current from somewhere. So the current must be flowing through this leg here, right? So our real thing we have to prove is that we have a high enough voltage here to turn that on, okay? But we saw here that this being on means it's pulling Q down to 0. So we have 0 volts right here, which by the way means Q is going to be a 0 answer, right? Looks like a donut. The 0 here is going to be at the top of this resistor. Since it is, that means there's no way this current could flow here, meaning this transistor right here must be off. And so if it's off, that means we have a high enough voltage here to turn that on. So we've demonstrated again that if this guy is on, this guy is off. So how do we know which one's on when we turn on the device? If we built this, how would we know which one was on? Rashana?
Based on the current flow?
No, I mean, if I were to sit down and bet you money, if I said, I bet you a penny that when I turn this on, the transistor on the left will be on, how would I know which one to bet on? Gabriel? Well, think of it as a black box. It's not turned on yet. All right, so I'm going to turn it on after we make our bet. So it's turned off. When I turn it on, one of those two transistors will be on, either the picture on the left or the picture on the right. Which one should I bet on?
Both.
That's I kind of like that. That reminds me of the cat in the closed box. But I have to bet on one or the other, or not play. I'm not going to play. And the reason I'm not going to play is because there's exactly the same chance that the one on the left or the one on the right will happen, given theoretical devices. Now, in the real world, one of them will actually probably always win because of the manufacturing process. One of those transistors is slightly faster than the other one. And they're both going to try to turn on at the beginning, or they're both going to try to turn off, depending on the exact design. One of them will win, and when it wins, it's going to force the other one off. So we don't know unless we've cheated and we've built the circuit and tested it many times in advance, and then we might have some sort of an edge to figure it out. But the odds of one, it is like Schrodinger's cat. We don't know if it's dead or alive till we look in the box. Until then, it's both of them. And so when we look at this, we don't have any way to know it. Now, the second question I would ask you is, okay, it seemed like this when I opened it up and I got it to work. This is what happened. Now I want it to do this. Which button do I push in here to make this change from a 1 to a 0? And the answer is this circuit is stable. You can't push any button. Once it goes into this state, it has latched in the value, never to be changed. Yeah, I could power it off and by chance the other one would come on, but that's a power on artifact. Once it's on and one of them is on, that one will stay on forever. That's what a latch does. So if we want the latch to be able to change, we need the third picture down here. We need to hook in to the bases of these two transistors some other signals. One we're going to call set, and the other we're going to call reset. So let's assume for a second that we had the picture on the right over here. We saw on the right, Q was a 0, and the transistor itself is fully on. So let me just mark on over here. We also know that for it to be on, we had to have a voltage here, like 5 volts, which is high enough to maintain it across that resistor, to turn it on and hold it on. This being 0 means this other guy had to have a 0 volts here in order to maintain it in its off condition. Because it's only when it's off that it has 5 volts here to keep the other one on. So what we need to do is we need to cause the world to be okay with us changing things. Basically, we're going to have to create an imbalance which will force it to the other transistor. So let's look at set and reset for a second. And I'm going to just color them blue for a moment, just for the heck of it. And I'm going to only use 0s and 1s instead of the voltages we've been using. Let's assume we have 0 here and 0 there. And we currently have the circuit set like it is. That means the 0 volts, which was here, drops across this resistor, drops across that resistor, because that's the only way current could flow, but it's still 0 volts all the way down. On this side, it was 5 volts. It needs to drop across a resistor to turn this on. We lose 0.7 there, but it has to drop all the way to ground to get here, but it can do that. So leaving these at 0 causes whatever state we have right now to be maintained. So I could switch it so this is on and that's off, and leaving it at 0 would do nothing. So let's take, we have a set signal and we have a reset signal. And we have Q. We just demonstrated that if both of them are 0, we have no change on Q. So we know there's 3 other things that could happen. Whoops. We could push reset, we could push set, or we could push both of them. Let's worry about that last one in a second, because that makes no sense. What we'd be telling it is we want Q to be both 0 and 1 at the same time. That makes no sense whatsoever. I'm going to mark it with a star and say that's illegal, that's disallowed. But I can push one or the other. Right now, what would we expect to happen if I pushed reset? Well, here's reset. So if I pushed reset, basically what I'm saying is I raise it to a 1. If I raise it to a 1, it supports the notion that this transistor should stay on. So basically, if I push reset and we're already reset, we'll just make a little note over to the side here that it stayed reset, okay? It was still on. So reset was, Q was still reset to 0. Let's take the other case where I'm going to push set, but I'm currently reset. So I'm going to push set. Well, when I force a 1 here, I'm going to force this transistor on. Now, during the time I'm forcing it on, that's going to pull this to ground, which means this will be 0 volts here, which means this transistor can't possibly be on. It has to go off. And Q can't have current passing here, so it has to come on and be set. So if I push set while it's reset, it actually set it. Make a note of that. But now that would mean, unlike a while ago when I pushed it while it was already reset, if I push reset while it's set, I should be able to change it. But let's first of all check what happens if I push set while it's set. Because remember, I released the button, it's still a 0. When it goes back to 0, this guy is still on because that guy is off and he's supporting him being on. So if I push set a second time, all it does is it just reinforces the notion this is on, just like reset did a while ago. So let's push reset again. Bring him back to 0, push reset. Well, if I push reset, this guy is now got enough voltage to turn on again. When he turns on, that means this line here gets pulled to 0, which means this guy's got to go off. And the off he has right here means it's going to support, when I release the button, it's going to support keeping this on. And this guy returned back to 0 again. So we've built exactly what we needed. If we do nothing, there's no change. If we push the reset, we're guaranteed at the end of that Q will be a 0. If we push set, we're guaranteed set will be a 1. And even when I release them, there's no change. So I can remember what the last button pressed was. Now, if I push them both, all bets are off. I would turn both transistors on. They would each try to support the other one being on. But when I released the buttons, the last one released would cause that transistor to be the one that was on. So I'd have a moment where things are disallowed. I'd have an unknown state, both transistors being on. So Q might be 0, it might be 1. But when I released it, the last one, last man standing, would be the one that would cause it to happen. And since I can't possibly release them at exactly the same instant, I could never leave it in a state where they were both maintained on. One or the other would always be left on. So we never use this last state. But what we've built is something called a set reset latch. It's often called an RS latch, sometimes called an SR latch, but they mean the same thing. So let's look at how we might build that if we were going to be using a TTL device. Now we're going to pay attention to the one on the left, not the one on the right, because the one on the right is going to be a little piece of homework for you. Okay, notice what I did here. I have NOR gates, not NANDs. The one on the right are NANDs. And we have two equations we have to worry about. One is the equation for a NOR gate. We have an A input, we have a B input, we have a Y output. 0, 0, 0, 1, 1, 0, 1, 1. Now, if it's a NOR gate, that means that anytime there's a 1, there'll be a 0 in the output. So significant points are having a 1 causes a 0. The only interesting number is this 1 we can get when both of them are zeros. So a couple interesting facts about it. Since we're using NOR gates and they're non-De Morgans, they're just plain old NOR gates. We notice what we've done. We've taken the output and brought it back to the input. This completely depends on there being propagation delay in this chip. Because if it happened instantly, we wouldn't get the new output. We'd get the wrong output sent back to us. So we have reset on top, we have set on the bottom, and what our notion is we have a RS latch, so we expect the table here, let me put reset first this time. We have reset and set, and they're generating two signals, Q and not Q. There's really two separate truth tables there. We could have them both not pressed. We could have only set pressed. We could have only reset pressed, or we could have them both pressed. The first case, Q doesn't change. So Q is simply going to be the same as whatever the previous Q was. Not Q will be the same. So it's just exactly the same value. Instead of writing it that way, I'm going to indicate it as N.C for no change. And he doesn't change either. Now, if we push reset, I'm sorry, set, if we push set, Q becomes a 1, not Q becomes a 0. If we push reset, Q becomes a 0, not Q becomes a 1. And the last state, of course, is disallowed. We can't push them both. We'll go to the engineers and see if they can design something better for us later. Okay, so let's see if that could be the case. Let's make the assumption when we turn this bad boy on, these have to be opposite each other. Let's just arbitrarily say Q is a 0. We have to demo that not Q is a 1, but that's what we would expect to have happen. So let's take and feed back these values into their respective NOR gates, meaning this guy has a 0 and something else. This guy has a 1 and something else. Remember what I said a while ago? Anytime there's a 1, here's a 0 for the output. So we know his output has to be a 0, regardless of what R is. So Q is reset no matter what R does. So if R is a 0, it's reset. If R is a 1, it stays reset. When we go back to 0, it still is reset. So what we need to be able to do is cause set to force the opposite thing to happen. Well, let's assume for a second I raise this to a 1. In our table, anything with a 1 has a 0 output. There's no longer a 1, it's a 0. If it's a 0 here, we're guaranteed, because the first row is a 1, to get a 1 out unless we make R be a 1 also. But we said we can't do that. That's disallowed. That bottom state is disallowed. So this forces this guy now to be a 0, and a 0 says it's the only time here that we get a 1 out if they're mixed, right? We can't have them both be 0s or both 1s in this case. And we get the 0 out. So, I'm sorry, get the 1 out. So by getting the 1 out, that means we're feeding a 1 back to this guy. And in our truth table, a 1, 1, or as we bring this back to 0, a 1 with anything forces the output to remain a 0. So pushing one of those causes Q to do the right thing. Push reset, Q becomes a 0. Push set, becomes a 1. If we push them both, we get a disallowed state, so we won't do that. If we don't push either one, the outputs don't change. Not Q is always the inverse of Q. Now, we could have built this exact same latch. This, again, is called an RS latch or an SR latch, depending on just your conventions at the time. But we have the NAND version of this. So I would encourage you for homework, and I'm not going to check it. This is where the people that are going to get A's ultimately get their A, is because they do the things I suggest you do, as opposed to the things you know I'm going to check. I'm not going to check this. You should build a NAND table. Right, so it's going to be A, B, and Y. And you fill it out, blah, blah, blah. You figure out which one the interesting ones are. And then you're also going to build an RS latch table over here. And at least do Q. You don't even have to do not Q because you know it's always the opposite of Q. But when you do this, one of the things that I'm going to give you a little clue of in advance is you're going to be kerplunking when you try to use the thing exactly the way it's been drawn in the book or the handout. What you're going to find is you're going to have a lot more success if you call this input not set, and if you call this input not reset. Not only did I reverse their position, I reversed their sex here on us. These are now the inverse. What that means is chances are pretty good, if we look at this table, that this is going to be the no change condition. This is going to be the don't do me condition. And this is going to be pressing set, is where set will go. And this is going to be pressing reset. So you'll need to play around with that and think about it. That's why I didn't start with this one, because this is a little clearer diagram. But this is a great homework problem for people that want to get an A in here, both of you. Okay, so let's move on to my next handout. And I'll post these online, of course, for you, so you don't have to copy everything down that we're doing. Of course, that's a terrible way to take notes, by the way, is to copy these diagrams down and try to stay up with me. A much better thing to do is write down what I'm talking about with this diagram as reference. And then immediately after class, putting that back together again. Okay, I talked about debouncing a switch. Here's a switch, has two positions. We could call them on and off or set and reset, but we're going to call them start and clear. When the switch is in this position, basically, clear will not be asserted, not clear will be asserted. When we move it to clear, clear will be asserted, not clear will not. It'd be used to cause a microcontroller system to start. We'd move it to clear the system, back again to start so it would run. Down to clear, everybody would see the clear signal, they'd know what to do, they'd clear all their inputs and outputs. When you went back to start, now they would be able to run again. Notice the switch can only be connected either here or here, not both places. And there's nothing connected to the one that isn't currently grounded. We know, since these are TTL chips, 7400s, that any unconnected input is treated as though it were a 1. We saw that when we went through the circuit for a 7400 chip. Also, I've drawn my NAND gates here as De Morgan gates, just to make talking about the problem, and when you do the analysis of that last circuit, make more sense, because you'll suddenly go, oh, I know why that did that on this picture. So let's see what happens here. If I take the signal, which is currently hooked to pin 1, and I drop it down and hit pin 5. That's this top timing diagram here. Pin 1 will suddenly go from connected to ground and immediately up to I'm not connected to anything, which means it's connected as though it were a 1. The other signal, though, is going to go to ground. But because this is a piece of metal touching a piece of metal, as it gets closer and closer and closer, little lightning bolts will jump back and forth between it until you touch it. No matter how fast you move it, you'll probably get some noise. That noise is, it was touched, it wasn't, it was, it wasn't, it was, it wasn't, it was, it wasn't, it was. So it may take that many pulses before it's stable. I've actually seen buttons where if you have a counter hooked to it, you can get over 1,000 counts before it becomes stable. So what we want to do is, instead of using pins 1 and 5 as being the start and clear signals, we want to pass it through this latch so that when the signal goes low, basically we moved it from pin 1 to pin 5, clear will go high, not clear will go low, and it will stay that way because we're using a latch until we move the switch again. It'll ignore all these extra pushes on the clear or not clear pin. Same thing happens again when we go back the other way. The other signal goes and stays high, but the other one gets a little lightning storm, but we've cleaned it up by making clear and not clear now have very stable latched values. You can see why that's useful. If I'm counting, the number of something, I want it to happen only when the switch is actually clicked, not on these artifacts that may follow. This is a result of real-time operation of a real circuit. You would really see these. And again, if we were having face-to-face, we would have built this. And you'd see the fact that, oh yeah, wow, I clicked that and we counted up a bunch of, things, and I thought I was going from 1 to 2. I went from 1 to 106. Why did that happen? Well, this explains it. Okay, next circuit. The circuit we had and we were looking at previously had one restriction to it, in that set and reset always made it through to the clear or the Q and the not Q. What if we only wanted to do that under control of a clock? So let's say that, I'll grab the edge of this and see if I can make it bigger so I can draw, but I'll shrink it down first. Let's assume that I had a 555 timer and it was producing a clock pulse thing that looked like this. And just for the heck of it, it's been running a while, so we'll pretend like it started with a low signal. Now, let's assume that S and R are changing signals. And we have a notion of when they change. Matter of fact, we have planned it in such a way that they can only change a set amount of time after a falling edge of a clock. So we can figure that S and R, I'll just put them as a single item here, can change somewhere while the clock is low, but can't change again until the clock is low again. And Jane, we talked about this earlier. Maybe stays the same this time. And we've told the rest of the system that it will be changed and being held stable anytime the clock is high. Well, here the clock is high. So that means anytime during that little window of time, during that little window of time, that window of time, and that window of time, I'm safe to read the value of whatever this is because I know it's being held stable. How we do that, that's a different problem. But we can think of S and R here as being this set of signals where when it's like this, R is low, S is high. Where it's here, it's the opposite. S is low, R is high. And we're doing them in pairs, but we're looking at that signal during those particular times. And we want to latch in either a set or a reset at that point. So what we could do is we could take 2 extra gates and hook them in front of what is basically a set reset latch. Then this part only works when this clock is passing a signal through. Remember the old block with an AND gate type of function? The clock becomes the thing that's doing the blocking. When it's low, this can't possibly pass a signal. When it's high, the signal completely controls what its output is. So by using the clock in this way, and this is a level clock, level triggered. We're able to only pass while the clock is high through the notion of set and reset. So Q and not Q can never change except during periods when the clock is high. And somebody else down the line is worried about the values of Q and not Q. They know they could only change when the clock is high, so we've built kind of a system of synchronization in using this type of clock. Okay, does everybody see that? Does anybody have a question about this particular picture? Okay. Actually, let me leave that up for just a second. You remember the picture without the clock for a second. Let's let the engineers get a hold of things here for a second. We took the clock back out, but our engineer got a hold of this, and he said, you know what? You've been using RNS for your signals, and you had a truth table which kind of said something similar to no change, set it, reset it, don't do it. I can protect you from this state right here. I'll just tie set and reset together and make one of them be inverted. That way you can never even get the first row of the table. You can't get the first row, you can't get the last row, but what you can get are those middle two rows. Isn't that what you wanted? I'll just call that signal D. I'll call it D for data. But again, good Star Trek reference there that I'll avoid. And we've got R and S as our outputs, but R is the inverse of S. Of course, we know there's some propagation delay and blah, blah, blah. We'll worry about that when we're designing our circuits. But they go into just a regular set reset. I notice with this that I don't have a clock. Because I don't have a clock in here to block the signal ever, do you notice that Q is always going to be whatever D is? Matter of fact, the equation for this is exactly that. Q is always whatever D is, because if D is a 1, that means set is going to be pressed and Q will get set. If D is a 0, that means reset is going to be pressed, and this will always be a 0. So thank you, Mr. Engineer, and you built something which I'm going to call a transparent. Don't know if I got enough time here to write this out in my lifetime. A transparent latch. And you know what? While this legitimately is what you say it is, I'm not going to ever use one of those. That's useless. Because all I did is have Q follow D. It's transparent, meaning I can see D through Q all the time. Whatever Q is, it's whatever D is right now. It lost all that latchiness, right? I didn't latch anything because D can't go away and have me remember it. Because if it goes away, I immediately see it. So although this is a D latch, you'd probably be hard pressed to go out and buy one of these because it's transparent and doesn't really do any functional things other than add some propagation delay. So how can we beef this up and still, because this actually is not too bad an idea. If we had a need to only get things when they're either set or not set, maybe there's a better way for us to latch it in rather than having to use a double set of inputs. Right here I can have a single button, whereas in the other one I definitely need two buttons, one for set, one for reset. Well, something we might do looks like this. I might put the clock back in. Now, actually, who wants to volunteer to tell me what this circuit does? Who wants an A? This is the who wants to be a millionaire? And I can give you the, is this the final answer?
I can try.
Okay, give it a shot.
This looks like it's just the D latch and the R/the clock combined.
Okay, that is exactly right. So what does it do differently than the last picture?
It functions the same as the last picture, except the D will only register if the clock is high.
You get the A for tonight, then I'll pass it to you. Unless somebody gets a better answer later, of course. But that's really good. That was a great explanation of that. He's exactly right. D will pass through to Q if the clock is high. Okay, so that's kind of useful because that's what we were doing with the JK earlier, right? And we do get the same effect of latching, but we only have to worry about one input. So this sounds like this has a lot of potential because lots of times I don't have something at its inverse available. What I have is something. So if I could cause Q to become D anytime the clock is high, of course, if D changed while the clock is high, it's transparent, I will see it. But if I could police D in such a way to keep it from doing that, then when I get to the end of D, whatever it is on the falling edge, I'll latch that in. Right, you could envision that even happening here. Let me grab the pinola here. So along I'm going here. And I got my clock signal doing this. And I got D doing funny stuff all over the place like this. And I'm not policing things very well right now. What I do know is Q is going to change all of those times. But it won't see this. Q will stay whatever Q previously had latched during this entire time period. But during here, Q will exactly follow whatever D is doing. At the point where this drops and becomes low again, Q will now become, let's assume Q started high. Q then is going to follow those signals exactly. And at the dropping edge, it's going to go to low and stay to low through this entire period here. So it can't be affected with changes while it's low, but it can while it's high. And the thing it latches in is whatever is there when the clock finally drops. So we could probably take advantage of that by knowing when the clock drops, but it would be better to keep the signal clean during the entire time that it's high like that. So what I'm seeing here is something that is kind of interesting. If I made the time that the clock is high bigger, I'm more likely to capture noise in that time period. Wouldn't it be better if I could somehow make sure that the clock always had a fairly small uptime? Because then I've got a much smaller window of time in which to have to hold D steady. Does everybody see that? That if the smaller I could get D, or smaller I could get the clock to be high, the less window I have where I have to hold D still. Now, of course, there are going to be some limits to that, but again, it's not really troubling to me because if I'm going to treat it like a latch, the thing I'm mostly interested in with this was not so much the fact it went high, but the fact it came low again. But if I could somehow make those almost be like a pulse, like that, every time I wanted to grab something, I'd be able to really kind of minimize the possibility of grabbing noise or having me to be too disciplined about how I held D. Now, we do have the ability to do that if we change the type of clock we have from a level clock to what we would call an edge-triggered clock. Now, this is specifically edge. I've used the word earlier to indicate a falling edge that had time around it. But in this case, basically, the pulse has no duration. We know it really does, but it goes high, and as minimum time it can, it drops low again. Wouldn't it be nice if I had a circuit element that upon receiving that particular set of things, it could generate a pulse up and it could generate a pulse down. And then because I'm only using 0 to 5 volts, I could throw away anything below ground. And I could grab pulses when they went high. That would be a really interesting thing. If only I had a circuit component that I could put something in one side of it, put a black box here for the moment, and I'd have something come out the other side. Well, if I thought of this as a function, the function really here is the same thing as a constant, because it has a constant value. The value I have over time here is basically 0. I could envision that if I were to go left one of these and say, if I had a function which went linearly uphill like that, and I wanted to generate a pulse out, those functions are related to each other in some way. Does anybody recognize the actual function that's being carried on there?
Differentiation.
You got it. We're taking the derivative of the function we receive. Now, if only we had a circuit component that knew how to do derivatives, that would be really handy. And I believe if you check your notes, we do have one. Let me fire up another copy of Paint here. When we arranged our capacitor and resistor in this elbow form like this, and we said we're going to take the output there, and the input's going to be taken basically across the base of this. I said any signal we put into here is going to have all the low frequencies blocked. So this is basically something called a high-pass filter. I'll just call it an HPF. And then I drew you another picture, and I said, well, if we reverse positions on them, and we took our output here, and we put our inputs in there. This one was a low-pass filter. And what it basically did is it took the resistance of this in series with the reactance of that, and since capacitors are frequency dependent, meaning the reactance changes depending on the frequency, low frequencies could pass through this, but high ones get blocked. In this case, low frequencies get passed through this, and high ones get blocked. Well, without doing the math here, that's exactly equivalent to what we do when we take the derivative of something. This is differentiation over here. This is integration over here. So if we could arrange in our circuit someplace in the clock where we could differentiate the clock we're receiving from the 555 timer, perhaps we could generate a pulse. And we can do that. If we put a high-pass filter here with our clock, instead of getting the square high piece, which remember is the thing that turns these on to let the thing pass, we now have coming out of the capacitor a pulse up, which is the same as this going up and staying there, except this one doesn't stay there. It snatches away from the D line, whatever D happens to be at the instant that occurs. It also gives us a pulse down, but because we're working with ground and above, we'll never see that particular pulse. The next one of these will occur, when we get the next rising edge. So now we can cause D to be latched into this thing at exactly the moment in time we get that pulse. And you can think of that pulse as being this rising edge right here. So we have an edge-triggered latch. Any edge-triggered latch is also called, and more properly called, a flip-flop. And this is one of the two most used sequential type of devices that do latching you're going to see, is a D flip-flop. Very, very popular chips, used a lot. Again, you open up the Space Shuttle or the Hubble telescope or your computer, you're going to find a bunch of D flip-flops in there, even if they're only emulated in other hardware. But what happens is we have an RS latch that is fronted with a clock. The clock has a differentiator on it, something that can take that pulse and turn it into a, or this, it's a pulse, but it's a long duration pulse, turn it into a very short pulse, which we can use the edge of to not block these gates, letting D and not D pass through as though they are set and reset to this latch. Setting or resetting Q and its inverse based on what D was at a particular point in time. That's very significant. We've saved D for some future reference. Won't change again until we get another pulse on the clock line. The very, very important circuit. You need to kind of in your head come back to this, and this is another homework assignment. I will probably ask you a question about this one in class. You'll probably be called upon to give me some numbers and things about this one. So I'd work my way through it. Okay, so this is an important one. We could write a truth table out for it. Remember, the truth table has only two inputs. It has D and a clock. D can only assume two values. Those two values, if we look right here, are the four possible inputs to the RS latch. Remember, because we could have them both zeros, but we've avoided that by inverting this one. We could have them both be all ones, we could have them all zeros, but they can't happen because the input signal has been engineered to either be D or not D. So we went from probably the most useless D latch possible to probably the most used flip-flop of its type, one that can actually save data for us at a specific point in time. Anybody have any questions about this particular picture? Okay. Let's look at another one. Now, to be very honest with you about the last one, this one takes it one further and probably is not as widely used, but is very, very much used. It's exactly the same as the last one, to here and to here. But we've inserted basically the original RS latch back in. So if you only look from here that direction, we basically have the same thing as our original RS latch, except now we've renamed the signal preset, which sets Q to a 1, and clear, which sets Q to a 0. These, however, are not under the influence of a clock. They are done, and I'll give you some terms here to use at the next party you go to. These are asynchronous. I'm just going to write async here. Asynchronous means without regard to a clock, where D is a synchronous signal, meaning it, although it can change any time, its value is only transferred with respect to the clock. Now, you will see that preset and clear can override the clocked stuff. So things that are asynchronous, if they happen, they override what's going on the clocked side of things. When would we use these? Well, normally when we turn a chip on, we get the same problem we had with the transistors or that first NAND gate I showed you. We don't know which way it's going to settle. We don't know if it's going to be settled with Q as a 0 or Q as a 1. We probably want to know. So we probably set up a button like that one that had clear and run. And when we put it to clear, that clear is attached to something like this. So it immediately causes this to turn Q into a 0, as does all the other D flip-flops in the system. When we release it, then Q will go back to being whatever is driven by D and the clock. But it can allow us to give some initial conditions to some outputs. We might want the initial condition to have been a 1. it can turn out that D flip-flops may have both, may have neither, or may have either one, or may even have some more bizarre third type of asynchronous signal available. We'll have to see as we look at other things. But this particular one, again, is something you need to understand the analysis for and be able to talk about if somebody were to ask you about it. Okay, let's go another flip-flop type. Notice this again would be called a flip-flop because the signal coming out of this differentiator here, or you could call it a high-pass filter, is going to be a pulse, not the high duty cycle time of a clock. So is it this guy or that guy? I think it's, let me see, is this the guy I just gave you? Yeah. Now, we removed the asynchronous and we removed the clocking mechanism in the way we had it previously. We've now gone back to the way we did it with the D flip-flop, with it being a real flip-flop. But notice we got rid of preset and clear, and we've renamed D to J and K. What? So we went back basically to the old R and S. We just gave them different names so that nobody would notice. Yeah, kind of. But we actually added some value here because we didn't wire it up quite the same way. This guy is still a clock, and he is going to cause J and K to do their thing only on the pulse. But remember, J and K kept as 0. I mean, now we have the case where we don't change anything even if we get a pulse. So now we can make Q retain even though we're getting pulses by simply leaving J and K low. But that still gives us that darn let's make J and K high. But you know what? The engineers thought of us. What they have done is they've rearranged the chart a little bit. And this is kind of interesting. And again, this is going to lead us, although this is not the second most popular. It's in the same family. I'll explain why it's not the most popular in just a couple of minutes. Okay, so now we've brought back that no change condition. We didn't really need that too much in the D flip-flop because generally we can control when we're going to snag a piece of data, but it is possible that we might have data changing multiple times and really only want to snag it once in a while. And then we could use J and K because we can leave it at don't change up until the point in time when we need to either snag it as set or snag it as reset. Remember, we can't hook J and K now to the same line like we could with D. So there's mixed uses for both of them. We did say, though, that if J is 0, Q is a 0. If J is a 1, Q is a 1. And that's when they're different. Now we come up with this they're both 1s. Well, the engineers thought of us here. What they did is they said, okay, let's feed back into those gates from Q back to the other gate, from not Q back to the other gate. And let's add that with the stuff that's already going on. And what that's going to give us is it's going to give us something we can call toggle. So that's kind of cool. What in the world could we do with toggle? Okay, let's take J and K on a flip-flop and wire them high, so they're both high. And let's put it right on the output of a 555 timer. Okay, you haven't seen the schematic for either of these yet, but let's just use a black box notation here. So here's our 555. And the only interesting thing about it is it has an output, which we're going to take and we're going to hook it up to the clock signal of the JK flip-flop that follows. And for whatever purpose, I'm going to take J, and I'm going to take K, and I'm going to just wire them to 1s. And then there'll ultimately be a box and some extra notation here, but eventually on the other side, I've got Q. And maybe not Q, and maybe a preset, maybe a clear, maybe other things. But right now, this is the thing I drew up here. I hook things up. I hook the output of a 555 to the clock, and then I wired J and K high. So let's assume that we've built a 555 timer in such a way that the duty cycle is a real mess. Oops, that's what happens on my machine. I'm going to try to keep it kind of short there. And picture these as being the same length high, even though I'm not doing a good job of that with drawing it. So this is the output of the 555 timer. Now we said that the output Q, so this is 555 output here. We said that the output Q of our JK flip-flop is going to toggle every time we have a rising edge. So let's assume it started low, it sees the rising edge and it goes high. Over here it sees another rising edge, so it's going to toggle. Over here it sees another rising edge, it's going to toggle. Another rising edge, it's going to toggle. Another rising edge, it's going to toggle. And so forth. Now, notice that if we look at the period of this, here's our first one. Goes there plus the little drop to the bottom. Here's the second one. There's the third one. This guy has a period which goes all the way there to there. So basically, it's twice as long as the original. So that means the frequency of this is 1/2 the frequency of that, which makes sense. We're doing something toggling every other one. So we've actually, let's say that this was putting out something at a frequency of 1,000 hertz. This would be putting it out at a frequency of 500 hertz. Let's also say that this had a 90% duty cycle. This one has a nice 50% duty cycle. And if we ran it into another flip-flop, say we had another one here, and it toggled every time it went high, it would toggle once here. It would toggle again when it goes high, here. It would toggle again here. So it once again is half the frequency. It would be at 250 hertz. And it would once again have an absolutely perfect 50% duty cycle. So we can clean up a 555's asymmetric pulse into a very even pulse. Often you want the even pulse because you're going to give 1/2 of it away to get yourself ready and the other half away to read the data. And you don't want a short period for either one of those. So typically what we might do in our first processor, we're going to build a 555 timer that is running at 2,000 hertz, which means we'll have one flip-flop behind it, which is going to generate the clock we use with the system, which is going to actually run at we won't have the third one, which runs at 1,000 hertz with a 50% duty cycle. So we'll have a near perfect clock to run our processor. We have to run this twice as fast, but the one we're actually using runs perfectly symmetrically. So we'll see that later and see why that's extremely useful, but you go look at your computer that you have. I guarantee you that your clock is not really, or the internals of your processor are not really running at that 4 gigahertz that's going in. It's getting pulsed down to a slower speed before it gets used. And on some machines that's significant, on others it's not much, but it can make a difference. I'll also show you later in the semester a way where we can actually get a faster frequency out of something that's going slow. We use something called a phase lock looped to make that happen, a PLL. But that's a different discussion for a different day. Now, this is great except for, you knew I had an except for. That's really hard to integrate on an integrated circuit. Capacitors are big and bulky. Resistors, not so bad, but it's much better at doing transistors and diodes. Because, and not that it's impossible to do this is possible, we're more likely to see a circuit. Now, the circuit, I will warn you, has a very unpopular name, which is master slave. And master slave anything is very tacky and not a name that should be used, but it is in the industry, and you'll see it on these things. Over time, this is getting changed, but the idea here is the first part is a controller. The second part behaves based on what the controller did, not on what the controller says. So when I refer to a JK flip-flop, normally the one I'm referring to is this one. I'll try to avoid using this just because it's insensitive. Now, the difference here is you'll notice there is no square clock being generated, right? Yeah, there is. Uh-oh, he lied to me. There is one. But there is no pulse clock. There's nothing looks like that. Well, when you have analyzed this, and I'm going to let you do that as homework, and this one I will check. I'm not going to make you turn it in, maybe. I might have you write something up and email it to me at the start of class next time. But you need to at least work your way through, and yourself, because you'll have worked through what's going on with one of these NAND gate latches, because here's one, and here's one. And what you got to figure out is, how are we managing to get a point in time so we can snag what J and K are intending at that exact moment in time? And you'll figure it out. I mean, you may have to talk to other people in the class to figure it out. But this is the second most popular chip you'll find, which is a JK of this variety. And it's used in places where you want to either continue generating something that looks like a clock, it keeps going with that toggle feature, or where literally the toggle feature and the ability to turn it on and off come into play. So I would say the two you're most likely to encounter are this one and this one with presets and clears, which will happen a lot, and the one over here that had the presets and clears but are a real D flip-flop. Now, I wouldn't worry about the fact that this would be hard to be integrated here. We can do that fairly easily by slightly modifying the circuit. And once you understand how the JK works, you'll be in pretty good shape. So I will give you a file containing all of these handouts that you can use for study. And we'll talk about these, and expect to be called on, because you probably will be, to talk about any of those. The two that were optional was understanding this one in great detail, but I would suggest to you it's probably a good idea. And also the one which was, I think it was this, where you're doing the right half on your own. You kind of need to do this in order, whoops, not that, to be able to understand what's going on here. Because if you notice, this is a NAND gate version of those. Notice that we have a third input. Don't worry too much about that. It just simply says that if this were an AND, if all three were on, the output would be a 1. Since it's a NAND, the output would be a 0. And the same thing applies down here. So kind of thinking about the uses of those and the things we have, that's a pretty good thing. I still have some more to cover on flip-flops and NAND gates. In particular, there's schematic diagrams and a couple little usage elements for them. And let me look at my notes here and see if there was much other than that we still had to do. Yes, schematics primarily. Oh yeah, and we need to go over the 7474 data sheet, which is a flip-flop that has things like propagation delay, but it also will have two other things in time that we need to talk about. I'll just really briefly on this, so we don't forget it, is when I have this pulse going on, I can't have and here's the signal I want to capture. My signal can't change at that exact moment. I have to have it in advance of that time by a little bit. That's called T sub SU, which is called setup time, meaning my signal actually has to be stable in front of the pulse some little nanosecond amount of time. Not only that, I can't remove it right away either. I need a T sub, maybe abbreviated H in ours. We'll have to look it up. but it's an amount of time that I have to hold it after the pulse in order to make sure it got read. So besides having propagation delay, which is the time it took to get from the output or from the inputs to the outputs, I also will have on anything that's clocked an amount of time I have to be set up in front of the clock and how much time I have to hold it after the clock to guarantee that the signal was actually snagged. So I got that. I've got the schematics and in detail about how we would use these in a circuit before we got to have all this under our belts well in advance of doing state machines because they're going to make heavy use of them. Okay, it looks like the big hand is on the correct numbers for us to be finished for the night. Does anybody have a question before we go or a comment?
Professor, I have a question about the picture. Did you say email or Blackboard?
These will all be on Blackboard and they'll be under lessons in a little file called ff.zip.
No, sorry, I meant the picture that we have to submit.
You're not submitting anything until I ask you to, and I'll give you instructions when you do.
Okay.
Okay, you just hang on to your own notes, and if we submit them, chances will be good it'll be done the same way we submitted the last things by email. But I also may simply ask you to take a poll. When I take a poll and don't show you the answers, I also can capture those, even though I was making fun of it tonight. So occasionally when I take a poll like that, what I'm really doing is not only recording your answer, which could be a very simple or difficult answer that nobody else is looking at the moment, but I'm also capturing attendance at that point in time. Okay, everybody tell everybody goodbye, and I will see you guys on Wednesday night at 6.
Bye. Thank you.
Good night.
Bye-bye.
Good night,
Wait a
Professor.
minute.
Thank you.
Bye.